Hey everybody, this is Mr. Ray with our next lesson in grade 12 data management. We are in Unit 3 where we're talking about probabilities, and today's lesson is a very, very important lesson. Most of the information here will be used later on in this unit and also in future units. So the concepts are carrying over. So it's very important to grasp this, to practice the homework questions, and to obviously to clarify any uncertainty. Calculations to calculate probability. So it'll be a fraction. Every calculation we do will involve multiple fractions, where the fraction comes from here. I'll just write it up here so it's nice and clear. So the probability of some event happening is the number of times it can happen over the total possibilities. Okay, so that's the key formula. The rest of these definitions we've all seen before in lesson 1 mostly of the unit. Some of the information down here, they mention again about using fundamental counting principles, and the fact that, well, you're going to have to remember about when we used adding versus multiplying when we're calculating things, and that all leads back to the wording of the questions. If you see something with the word "and" in between two calculations, that both of those things have to be true, then you're going to multiply the counts together. If you see the word "or," where you're combining those two counts, well, it could be one or the other. So in that case, you're going to add. Okay, so those are skills hopefully you've carried over from Unit 1. Also, the thing you're going to have to understand is permutations and combinations. Remember the key, I think the key thing we learned there about how do you choose whether or not you use a permutation or combination. If the order is important, then use a permutation. If the order is not important, use a combination. And you'll get both types of questions, so you have to be very clear on which one you're going to use. Obviously, you'll get the wrong answer if you use the wrong type. Okay. All right, so we're going to have, I believe, 5 questions for examples. Go through them. Hopefully that brings a pretty good understanding of what's going on with this method of counting to calculate probabilities. So, first question, 2 brothers enter a race with 5 friends, so a total of 7 in the race. The racer draws lots to determine their starting position. So it's basically, you're picking, each of them pick a number from 1 to 7, and that will determine where they line up for the race in lane 1 up to lane 7. Okay, so what are we being asked here? What's the probability that the older brother will start in lane 1 with his brother beside him? And that kind of infers that's lane 2. So, since I'm finding that probability, I want to define that event right from the beginning. So A is going to be when the older brother is in lane 1, or I'll call it P1, and younger brother in P2, or lane 2. Okay, now for something like this, and if you remember back when we did combinations and permutations, any kind of little sketch to help you figure it out is useful. So I'm actually going to do my boxes. So each box will represent a lane in the race. So I've got 7 of those. So this will be lane 1, 2, 3, 4, 5, 6, 7. Okay, so what has to happen here? Well, we want the older brother to be in lane 1. So I'm just going to call him B1. And then the younger brother's in lane 2, so B2. So those 2 guys are fixed in order what we're trying to calculate the probability of the 2 brothers in here in that specific order. And then the other 5 positions here can be filled up by the 5 other racers. So 5 other racers here. Okay, so just like when we learned permutations, how many choices do I have for lane 3? Well, I no longer have these guys, but I have all 5 of these guys still. So I have 5 choices for lane 3. Lane 4, I've used one of the 5 for here, so now I have 4 choices, 3 choices for the next lane, 2 and 1. Okay, so basically the answer, the number of ways that they can line up with the brothers in the right position will be 5 times 4 times 3 times 2 times 1. Now, what I'm going to do, so the number of times that can happen, I'm going to put this in terms of a permutation. I mean, you can get the answer straight from here if you want, but it is a permutation because the order is important. Each different order is a different lineup for the race. So in this case, it is important. That's why we use permutations. So if I'm using permutations, it's how many ways can I pick racers in these 5 lanes. So pick five racers in the 5 lanes. So that's just 5p5, 5 pick 5. And if you remember the formula for that, that just works out to 5 factorial, which is exactly what this is, 5 factorial. So that works out to 120. Now, in order to do the probability, like in unit 1, we just stopped here. How many ways can these guys line up? And we just got that answer. So now we're doing the probability. So now on the bottom of the fraction that I'm going to use for probability, it's the total number of ways these 7 guys can line up. So what are all the what are all the possible lane assignments, different lane assignments for these 7 guys? So in this case, it's permutation, but this time I'm also moving the 2 brothers. I'm including them in the possible arrangements. So this is going to be 7p7, 7 pick 7, which is 7 factorial, which is that is 5040. So now I can do the probability. Remember, the probability of A happening is the number of times A happens over the total number of all possible ways this experiment can happen. So that's NS, so that's 120 over 5040, and this can be reduced to 1 over 42. You could also reduce it with the factorials, because basically this is 5 factorial over 7 factorial, so you basically have just a 6 and a 7 left here when you cancel out the 5 factorials, which is 42. So I'm going to leave it like that. Maybe I'll just put a little therefore the probability of this lane assignment is 1 over 42. You could change that to a decimal or a percentage, but that's exact. Okay, so that's how you do it. So again, we just use the concept that we had earlier. How do we calculate the probability of something happening? It's the number of times it happens over the total possible ways this experiment can happen. In this case, the experiment was assigning lanes for the 7 racers. Okay, next question. A focus group of 3 doctors is to be randomly selected from a medical team consisting of 5 doctors and 7 technicians. So basically, you got 5 doctors, 7 technicians. You're going to be choosing 3 of these people to be part of a focus group. Okay, so first part, what's the probability that the focus group will be comprised of doctors only? So in the original part up here, these groups, focus group, you could have any number of, you could have all doctors, you could have all technicians, or anything between that, where you have 1 or 2 from each group. So what's the probability that the focus group will be comprised of doctors only? So again, define our event A. So what are we trying to find here? Probability the focus group will be comprised of doctors only. So the event is the focus group has only doctors, or I could just say has 3 doctors, because that's the size of the focus group. Okay, so how many different focus groups could we have that are comprised of all doctors? So this is where, again, you have to think, is this a permutation or combination? So when you talk about a group of people, does it matter which person I pick first in the group? And since there's no defined roles in this focus group, it's just a collection of people. So in this case, it doesn't matter in which position I pick them, whether I pick them first, second, or third for the group, it doesn't matter. So this is a combination because the order doesn't matter. So when I'm talking about how do I select my, so I'm going to select my 3 doctors to be on, and I have 5 doctors to choose from. So I'm going to take those 5 doctors and choose 3, so that's 5 choose 3. That's the number of ways I can choose 3 doctors from the 5 that are there. Now, I've also got, and you don't have to put this, and I'll talk about it in a second, but how many ways can I choose the technicians? And you may say, well, we're not choosing any technicians. Well, I could put that here. I've got 7 technicians, and I'm going to choose 0. Okay, so how many ways can you choose 0 of anything? It's always going to be 1. So basically I'm multiplying by 1. So did I really need to put this here? Not for the accuracy of the answer, but I could make a minor change to this question, and you could look at this formula and easily adapt this to the new question. So I'm putting it in just for that, but it doesn't change the answer if I leave it out. So 5 choose 3, that's 10. And 7 choose 0, we said that's 1. So the answer is 10. There's 10 ways to pick our our focus group if all of the focus group, all 3 of them are doctors. So there's 10 ways. And then we have to figure out what's the total number of possible committees with no restrictions. So in this case, we're actually, it doesn't matter whether you're a doctor or technician, you're considered to be equally able to join the group. So how many people do we have to choose from? 5 plus 7, that's 12. So I got 12 to choose from, and I'm going to pick my focus group of 3. So 12 choose 3, and that's equal to 220. 200 ways to pick any. 220 different focus groups from those 12 people. So now when I do my probability of A happening is, and you don't have to put this every time, but I'm trying to drill it in so you understand every time. the number of times A happens over the total possible ways the experiment could go. So in this case, it's going to be 10 over 220, which is equal to, if I divide by 10, 1 over 22. So the probability of only doctors chosen is 1 over 22. Okay. Part B, what's the probability that the focus group will not be comprised of doctors only? So you may read that and go, well, we kind of sort of answered that in the last question, but we answered the complement. Okay, so this is asking what's the probability that it's not all doctors. So you could go through this again as if you you didn't really relate what you just did, or you could say, you know what, I'm going to define my complement group for A, where it says focus group well, it doesn't have 3 doctors, it's going to have 0, 1, or 2 doctors. So that's, that's a complement of A. So, and I could calculate the number of times that happens, but this is actually a very complicated calculation to get to count how many times this can happen. But what we're going to do is take a shortcut, because we've already calculated the probability of A happening, and we're asked to calculate the probability of A prime or A complement happening. So there's a nice formula for that. The probability of A prime is equal to 1 minus the probability of A. So because those two probabilities of it happening or not always equal 1, so if you want to get the other one, if you knew one of these, to get the other one, you just subtract it from 1. Okay, so we take our 1 and subtract the probability we got from here, 1 over 22, so that's, if we leave it as a fraction, that's 21 over 22. So I'll just leave it like that. I won't put a word answer this time. But you can see that these, so there's, 1 out of 22 times you'll get 3 all doctors, and the other 21 out of 22 times you'll get less than 3 doctors on the committee, 0, 1, or 2. Okay. Now, actually love this question. It's one of my favorite questions from data. Not so much in the technique, but the surprise it brings. Okay, so question is, what's the probability that 2 or more students out of a class of 24 will have the same birthday? Assume that no students were born on February 29th, which is the leap day. This just makes all the years, we'll just assume they're out of 365 and nobody had a birthday on that date. So anytime I do this in a class, I'll ask students what they think the probability is of 2 or more students sharing birthdays, and including myself, you would expect this to be probably pretty low. I think the first time I looked at this, I was predicting 5 to 10% maybe. It just seemed, there's 365 possible birthdays, and we've only got 24 people here. So it seems unlikely, more unlikely, that they don't share a birthday. So, so the results will be surprising, as a little hint to what we're going to get here. So let's dive into this. Now, don't get too concerned with the math here. This is a fairly complicated question. I'm sure some students in the course could get it, but I don't expect, I wouldn't give this question again, but I want you to see the technique, because there could be something on a less complicated version of this with the same sort of technique. So I want you to be able to understand it, but not so much worry about, oh, I never could have got that. Okay, so we're going to start with the probability of the two students. So we'll start with a low number here. Probability that two students don't share a birthday. Okay, so let's start with the other thing. What's the probability that two students do share a birthday? So assume you've got the first person, you know their birthday. What's the probability that the second person has that same birthday? Well, that's 1 day out of the year. So probability that they do share a birthday would be 1 over 365. So the complement of that, probably they don't share a birthday, would be 364 over 365. So very high probability that those two people don't share a birthday. So we're going to extend this. We're going to keep going. What about 3 students? What's the probability 3 students don't share a birthday? Okay, so we're going to start off with what we already know. You have to start off with what's the probability that the first 2 don't. So don't share a birthday. So that's the same as what we just did. And now that we know that those 2 don't, then we take the third person. And what's the probability that third person doesn't have the same birthday as the other 2? Well, we already know the other 2 don't share a birthday. So there's 2 days. There's already 2 days that you know that this person, the third person, can't have their birthday on. So if we take away those 2 days from the 365, we get 363. So the probability that the third person doesn't have the same birthday as the other 2 will be 363 over 365. So again, it seems these are very, very high numbers. They're very close to 1. You'd figure that, okay, well, it's almost no possibility that those 3 would share a birthday. And we'll just do this one as well. Probably the probability that 4 students don't share a birthday. We're going to just keep going on this. So it's kind of an iterative process. So the probability that the first 2 don't share a birthday, and then that the third person doesn't have the same birthday as the first 2 is that. And then the fourth person, what's the probability that he or she doesn't have the same birthday as the first 3 people? Well, we take away the 3 dates from the first 3 students, so we're down to 362 over 365. So you can see the pattern here. The denominator just stays the same, number of days in a year, and as we progress here, we're lowering the numerator by 1 each time. Okay, so if I kind of jump down to the probability of 24 students don't share a birthday. Okay, well, I'm going to continue this pattern here. So I'll just put the first 2 times 363 over 365, and then I'll do the old famous dot, dot, dot. And then the last term, that's the one we have to come up with. So this would be, the probability that the 24th person doesn't share the same birthday as the previous 23 people. And you can see from the pattern, you already know the bottom, 365. Okay, so we can't use the previous 23 days of the birthdays of the first 23 students. So we're taking out 23 days from there. So that's 365 minus 23, that's 342. Okay, so basically the probability that the 24 students don't share a birthday is this calculation. It's a pretty intimidating calculation. So let me, okay, I'll just continue that. Okay, so you can see on the top I've got 364 times 363 times dot 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 down to 342, And then on the bottom, I got 365 times itself. How many times? Well, how many terms do I have here? That would be, I believe, 23. So this minus this. Yeah, it's 23. So this will be 365 to the power of 23, which is a huge number. I'm not sure many calculators could do that. Now on the top here, I could actually put this as a permutation. Okay, so the number on the left will be the 364. And then to get this factorial to stop at 342, I'm going to have to make this a 23 here, because then that would be 364 factorial over 341 factorial, which would leave you that. Okay, and then the bottom's still the same. Now, I'm not going to worry about, how do I calculate that. If you did calculate that, you would get this number, 0.493. Okay, so let's remember what this is. This is a probability that 24 students don't share a birthday. Okay, so if I want to know the probability of the 24 students have at least one shared birthday, okay, that's going to be equal to, again, remember the complement of the probabilities. That's 1 minus 0.493, which is equal to 0.507. So that's the probability we're looking for. Probability that in a class of 24, probability that at least one birthday is shared is 50.7%, which is, actually more than likely to happen. And as soon as you start adding more people to the class, obviously, if you had a class of 30, I don't remember the exact number, but it bumps up to maybe 55, 60%. Now, if you had a class, well, I guess it wouldn't be a class. If you had 365 people, that would mean that, well, I guess 366 would be the magic number. 366 people, you have to have at least one shared birthday, because, well, I think that's apparent. So you will reach a probability of 100% as soon as you have 366 people, but it does get pretty high well before that. So I found that to be a very interesting question. When I teach this in class, I'll go through the class of, say, 30 people and ask each student one at a time to say their birth date, and if somebody else shares their birthday, they have to kind of shout out, that's my birthday too. And I think for the last five years I've done that, I think we've had at least one shared birthday. We kind of stop when we get to one, but could easily be more than one. Okay, the last two examples have to do with probability of getting a certain hand in a card game. This is a fairly common type of question, so I wanted to get you some feeling for how this works, how you'd actually calculate probabilities of getting a certain hand. So this example here, what's the probability of drawing a flush? 5 cards of the same suit. So hopefully everyone remembers 52 cards in a deck, 4 suits of 13 cards, clubs, diamonds, hearts, spades, and basically the cards for each suit go 2 up to 10, then Jack, Queen, King, Ace. Okay, so what's the probability of drawing a flush? So we're going to define our event A as being dealt a flush, or drawing a flush. So basically it means that all your cards are the same suit. Like they could all be clubs, they could all be spades, or they could be diamonds, but you'll have no other no other cards of a different suit, obviously. So I'm going to count the number of ways you can be dealt a flush. So that's NA. How many times can you get a flush? So this is counting techniques, which we learned in Unit 1. So the first thing we have to do is, at least for this type of hand, I could get a flush in any of the 4 suits. So I actually have to choose the suit because, well, you'll see it in a second. So to choose the suit, I've got 4 suits to choose from, and I'm going to choose one. So 4 choose one. So that gets me the suit. And then I want to pick 5 cards from that suit, or from a suit. Okay, so how many cards in a suit? There's 13 cards in each suit, and I want to choose 5 of them. So this is to choose the suit. This is to choose the 5 cards in the suit. Okay, and because you heard the word "and" a couple of times, because it's "and," you multiply the 2 results. Okay, adding. So when I do this, I get 4 for the, and that makes sense. There's 4 different suits I can choose, and there are 1287 ways of picking 5 cards from 13. And you notice, I'm using combinations because it doesn't matter. Do I get the 7 of clubs first or 5th when I'm being dealt the cards? It doesn't matter because when I put my hand together, it doesn't matter. We just kind of count up the cards and move them around at that point. Okay, so if I multiply that, I get 5148. So that's the number of possible flushes. And then we want to know NS. So in this case, NS is what are the total number of hands that I could get? Just randomly 5 cards picked from a deck of 52, chosen from. So that's going to be 52, choose 5. Again, doesn't matter the order, choosing 5 cards from 52. And this is equal to 2,598,960. And this is a very famous number. You'll see it quite often because anytime you do probability of getting a certain hand, this will be your denominator because that's the number of hands that are possible. Now, to get the probability of getting a flush, I just take those 2 numbers and use them. NA over NS, so that's 5148 over 2,598,960, and you can see it's pretty low fraction there. It works out as a decimal to 0.00198, which is about 0.198%. Okay, so that's a pretty low chance of getting a flush, and that's why if you do get one, it's a good hand. You consider it to be pretty lucky. Okay, we'll do another type of hand here. What's the probability of drawing a full house? So if you don't know what a full house is, it means 3 of the 5 cards are the same number or same type of card. It could be 3 jacks, 3 2s, 3 aces. Okay, and then the other 2 cards are also the same number. Okay, they can't all be the same. That would be impossible because you've only got 4 suits, so you can't have 5 aces unless you're cheating. But this could be something like 3 sevens and 2 jacks, or it could be any combination of the different types. So again, we'll define our event. Our event will be being dealt a full house. Okay, So let's talk about how many ways can we get a full house. So this is a little different than the first one. We're going to break this down into two parts. How many ways can I get 3 cards the same? And then we'll deal with the other 2 cards after that. Try to narrow it down, work your way through it. So how can I get my 3 of a kind? So now those 3 cards have to be the same card number, like a 2 or a 7 or a queen. So there's 13 of those. So I'm going to start off with 13, choose 1. So that gives me the whichever card that I have 3 of. Okay, 13, choose 1. And then now if you think about it, I'm going to have 3 of those types. Okay, but there's actually 4 suits. So how many ways could I get, say, three jacks? Well, since there's 4 jacks I can choose from, or whatever type of card number I have, I'm going to have 4 jacks. I'm going to choose 3 of those because it's 3 of a kind. Okay, so this gives me the card number, and this gives me the 3 suits of those 3 cards. How many ways can I pick 3 suits from 4? Okay, so this gives me my 3 of a kind. How many ways can I get of 3 of a kind in a hand? Now, so I could put this in brackets just to separate it, but now I'm going to multiply because it's 3 of a kind and 2 of a kind. So now I calculate my 2 of a kind here, and it's a little similar to this, but a little bit different. So if I'm going to pick the type of card I have for my 2 of a kind, it can't be the same as the one I picked here. So now I only have 12 card types to choose from, and of course I'm choosing 1 of those 12. Okay, and then so that gives me the 4 or the ace or whatever I picked. Okay, now it's the same idea as this. How many, like I'm picking 2 of these because it's 2 of a kind, but I have 4 suits to choose from. So 4 choose 2 will give me the 2 suits of that type of card that I have 2 of. Okay, so this is my 2 of a kind calculation. Okay, now that's equal to, well, these are nice and easy. That's a 13. 4 choose 3 is 4. And then I have 12 choose 1 is 12. 4 choose 2, that's actually 6. Okay, so that's 52 plus 72, or sorry, 52 times 72, so that's 3744. So that tells me there's 3,744 different full houses that you could be dealt. That's a lot. Okay, now I want to get how many hands could I be dealt? Well, I already know that from the previous question. 52 choose 5, that's 2, 5, 9, 8, 9, 60. See, we used that twice already, so I told you it was a very commonly used number. Now to get the probability of A happening, that's going to be NA over NS, which is 3744 over 2598960. That's equal to 0.00144, which is equal to 0.144%. Okay, so there's our answer. And you could be asked, well, a good question might be, what kind of hand are you more likely to be dealt, a full house or a flush or a full house? And you could just look at these percentages here. So there's the probability of getting a flush. There's the probability of getting a full house. So a flush is more likely to get than a full house. Okay, So that's how we use the counting technique um, to predict probabilities of things happening. So I've got some practice questions here in the homework. So please work on them, and we'll continue on the next day with another lesson on calculating probabilities. So have a good day.